Hello everyone. I'm Snega Priya, Assistant Professor, Department of Information Technology. Today we have to learn about virtual memory and demand paging in operating system. First, we have to know about virtual memory. Virtual memory is a technique that allows the execution of processes that are not completely in memory. The advantage of the scheme is that programs can be larger than physical memory. Further, the virtual memory abstracts the main memory into an extremely large uniform array of storage and separating logical memory as viewed by the user from physical memory. So, this technique free programmers from concerns of memory storage limitations. So, virtual memory, which also allows the processors to share files easily and to implement shared memory, and virtual memory is not easy to implement, however maybe sustainably decrease performance if it is used and carelessly. Okay, so this is a virtual memory. Okay, so why we are need a virtual memory? So let's we discuss about why we need the virtual memory for the operating systems. The programs often have code to handle unusual errors conditions. So since these errors seldom if occur in practice, this code is almost never executed. Okay, so arrays, lists, and tables are often allocated more memory than they actually needed. An array may be declared 100 by 100 elements, even though it is seldom larger than 10 by 10 elements. As assembly symbol table may have room for 3000 symbols, although the average program has less than 200 symbols. So certain options and features of a program may be used rarely. For instance, the routines of computers balance and budget have not been used in many years. So a program would no longer be constrained by the amount of physical memory that is available. So users would be able to write programs for an extremely large virtual address space and simplifying the programming task. Because each user program could take less physical memory, more programs could be run at the same time with a corresponding increase in CPU utilization and throughput, but with no increase in response time or turnaround time. Okay, so less IO would be needed to load or swap user programs into memory. So each user program would run faster. Thus, the running a program that is not entirely in memory would benefit both the systems and users. So, what the virtual memory involves in it will separation of user logical memory from physical memory as specified by users from physical memory. So the separations allows an extremely large virtual memory to be provided for programmers when only a smaller physical memory is available. So following figure can explain that virtual memory makes the task of programming much easier because the programmer no longer needs to worry about the amount of physical memory available. So he or she can concentrate instead on a problem to be programmed. So we have to know about the virtual address space. The virtual address space of a process refers to a logical or a virtual view of how a process is stored in a memory. So typically this view is that the process begins at the certain logical address, say address 0, and exits the contiguous memory as shown. Okay, so the following figure will explain how the virtual address space to be processed. Okay, so this is the figure. Okay, so this will says about how the organizing the page frames, that the physical page frames assigned to a process may not be used as a virtual memory. So here it is up to the MMU, that is memory management unit, to map logical pages to physical page frames in memory. So this figure will explain uh, how the virtual memory that is larger than the physical memory. Okay, so a program would no longer be constrained by the amount of physical memory that is available. So users would be able to write programs for an extremely large virtual address spaces, simplifying the programming task. Virtual memory makes the task of programming much easier because the programmer no longer needs to worry about the amount of the physical memory available. Okay, so next, virtual address space. So usually virtual address space is similarly allow for the stack to grow downward in memory through successive function calls. So the large blank space or hole between the heap and stack is part of the virtual address. Okay, so the space but will require actual physical pages only if the heap or stack grows. So virtual address spaces that include holes are known as sparse address spaces. Using a sparse address space is beneficially because the holes can be filled as the stack or heap segments grow, or if we wish to dynamically link libraries for possible other shared objects during program execution. In addition to separating logical memory from physical memory, virtual memory allows files and memory to be shared by two or more processors through page sharing. So, the virtual address space leads the following benefits. What are they? We will follow that. First one is the system libraries can be shared by several processes through mapping of a shared object into virtual address space. Although each process considers the shared libraries to be part of its physical memory, virtual address space. The actual pages, which are libraries, reside in physical memory or shared by all the processes. Okay, so this is how it will work. Okay, this is shared library using virtual memory. So typically, the library is mapped read only into the space of each process that is linked with it. So similarly, virtual memory enables process to share memory. Recall. The user can share memory. Virtual memory allows one process to create a region of memory that it can share with another processes. So process sharing the region consider it part of their virtual address space at the actual physical pages of memory are shared. Okay, so another benefit of the virtual address space is the virtual memory can allow pages to be shared during processes creation with the fork of system call method. Okay, so though this it is speeding up process creation, so it will used for a process creations during the process creations to be shared by the virtual memory. Okay. So next we have to learn about demand paging. So first we have to know about the demand paging. So consider how an executable program might be loaded from disk into memory. One option is to load the entire program in physical memory at program execution time. However, a problem with this approach is that we may not initially need the entire program in memory. Suppose a program starts with a list of available options from which the user is to select. Loading the entire program into memory results in loading the executable code for all options, regardless of whether an option is ultimately selected by the user or not. An alternative strategy is to load pages only as they are needed. This technique is known as a demand paging and it is commonly used in virtual memory systems. With demand paged virtual memory, pages are only loaded when they are demanded during program execution. So, pages that are never accessed or thus never loaded into your physical memory. Okay, so a demand paging system is similar to a paging system with swapping. Okay, so this is the diagram where process reside in a secondary memory, which means usually in your disk. When we want to execute a process, we swap into it a memory. Rather than swapping the entire process into memory, how we use lazy swapper. A lazy swapper never swaps a page into memory unless that the page will be needed. Since we are now viewing a process as a sequence of pages rather than as a one larger contiguous address space. Use of the term swapper is technically incorrect. Okay, a swapper manipulates entire processes, whereas a pager is concerned with the individual process. Pages of a process. So we thus use pager rather than the swapper in connection with the demand paging. So this diagram will explain the transfer of paged memory to contiguous disk space. Okay, so program A and program B is there. This is swap out and swap in process to be performed in this demand paging. Okay, so so this is a basic concept in a virtual memory. Okay, so that is page table. When some pages are not in the main memory, and steps in handling the page fault. So these are the concepts we learn further. So when a process is to be swapped, the pager guesses which pages will be used before the process is swapped out again. Instead of swapping in a whole process, the pager brings only those pages into memory. So thus it avoids reading into memory pages that will not be used anyway, decreasing the swap time and the amount of physical memory needed. With this scheme, we need some from the hardware support to distinguish between the pages that are in memory and pages that are on the disk. The valid or invalid bit scheme described. So this can be used for this purpose. Okay, so this time, however, when this bit is set to valid, the associated page is both legal and memory. If the bit is to be invalid, the page either is not valid or is valid but is currently on the disk. So the page table entry for the page that is not currently in the memory is either simply marked invalid or contain the address of the page on disk. So this situation is depicted in this figure. Okay, so this is a valid and invalid bit. So with each table entry, a valid and invalid bit is associated with an memory, that is V in memory, and memory resident is I, that is not in memory. Okay, so invalid bit is set to I in all entries, and this is a page table snapshot. Okay, so during MMU addresses translation. If valid or invalid bit in page table entry as I is a page fault, which means a memory resident is a page fault. Okay, so the marking a page invalid will have no effect in the process, never attempts to access at that page. So if we guess right and page in all and only those pages that are actually needed, the process will run exactly as those we had abroad in all pages. While the process executes and access pages that memory resident and execution process normally. Okay, so page table, when some pages are not in mind memory, so this is a page table, and logical memory and physical memory is there. Okay, so some of the pages is not in the memory, not in the main memory, but it is in the physical memory. Okay, so next we have to learn about discuss about a page of fault. Okay, so page fault, if there is any reference to a page, first reference to that page will trap to operating system. It is a page fault. Okay, so operating system looks at another table to decide if it is an invalid reference. It will abort that page. Okay, uh, if it is an valid just in a memory, so find frame and swap page into frame via scheduled disk operations. So reset tables to indicate page now in memory. Set validation bit is equal to V, and restore the instruction that caused the page fault. Okay, so but what happens if process tries to access the page that was not brought into memory? So access to a page marked invalid cause the page fault. So the paging hardware and translating the address through the page table will notice that the invalid bit is set, causing trap to the operating system. So this trap is a result of the operating system failure to bring desired page into memory. So we have to there is a page fault is straightforward operation. So the procedure for handling this page fault. Okay, so there are six steps over there. So first we have to check an internal table, usually kept with the process control block. Okay, so for this process to determine whether the reference was a valid or invalid memory address. Okay, so if the reference was invalid, we terminate the process. If it was valid but we have not yet brought in that page, we now page it in. Okay, so next one is if the reference was an um, if its reference was an invalid, we terminate the process. If it was valid but we have not brought it that page, we now page it in. So we find a free frame by taking one from the free frame list. Okay, so we schedule a disk operation to read the desired page into the newly allocated frame. So next one is when the disk read is completed, we modify the internal table kept with the process and the page table to indicate that page is now in memory. Okay, so next we restore the instruction that was interrupted by the trap. The process can now access the page as through it had all been in memory. So in the extreme case, we can start executing a process with no pages in memory. When operating system says the instruction pointer to the first instruction of the process, which an on non-memory resident page. Okay, so we have to brought into memory. There is a page is brought into memory, and the process continues to execute faulting as necessary until every page that is need is in the memory. So at that point it can execute with no more faults. So this scheme is pure demand paging. So never bring a page into memory until it is required. Okay, wow. So and then we have to know about the page table and secondary memory. So page table, this table has the ability to mark an entry invalid through a valid invalid bit or special value of protection bits. So secondary memory, this will hold those pages that are not present in main memory. The secondary memory is usually high speed disk. It is known as the swap device, and the section of disk used for this purpose is known as swap space. So the circular requirement of demand paging is ability to restart on any instructions after the page fault, because we save the state, that is registers contain code instructions counters of the interrupted process when the page fault occurs. So we must be able to restore the process exactly so the same place and the state, except the desired page is now in memory and it is accessible. Okay, so a worst case example, consider the three address instructions such as add and constant to A to B, placing the results in C. So these steps to execute these instructions: first fetch and decode the instruction, add and fetch A, fetch B, add A and B, and store the sum in C. So if we fault when we try to store a C, we will have to get the desired page, bring it in. So correct the page table and restore the instruction. The restore will require fetching the instruction again, decoding it again, and fetching two operands again, and then adding again. However, there is not much repeated work, and the repetition is necessary only when a page fault occurs. Okay, wow. And then the performance of demand paging. Okay, so demand paging can significantly affect the performance of a computer systems. So to see why, let's compute effective access time for demand paged memory. Okay, so for most computer systems, the memory access time, denoted MA, ranges from 10 to 200 nanoseconds. As long as we have no page faults, that effective access time is equal to memory access time. If, however, a page fault occurs, we must first read the relevant page from the disk and then access the desired world. So let P be the probability of the page fault. Okay, so then 0 is less than or equal to P and less than or equal to 1. So we could expect P to be close to 0. So that is, we would be expect have only a few page faults and the effective access time is same. Hmm. An extreme case is what processes no pages in memory. So always set instruction pointer to first instruction of processes as a non-memory resident page fault. And for the every other processes pages on first access, a few demand pagings to be done. Okay, so here there is a instruction restart. So consider an instruction that could access several different locations, that is block move, auto increment or decrement location, and restore the whole operation what if those destinations overlap. So the performance and the band paging, the page fault causes following the sequences to occur: trap the operating system, save the user registers and process state, and determine that the interrupt was the page fault. Check the page difference and legal and determine the location of that page on the disk. Issue a read from a disk a free frame. Wait in a queue for this device until the read request is serviced. Wait for the device seek and latency time. Begin the transfer of the pages to a free frame. While waiting, allocate the CPU to some other user. CPU scheduling is optional. So receive an interrupt from the disk or IO subsystems. So save the registers process state for the other users and determine that the interrupt was from the disk. Correct the page table. Another table is to show desired page is now in memory, and wait for the CPU to be allocated to this process again. Restore the user registers process state and new page tape, and then resume the interrupt instruction. Okay, so not all these steps are necessary in every case. For example, we are assuming that in step 6, the CPU is allocated to another process while the IO occurs. So, this arrangement allows multi-programming to maintain CPU utilization but requires additional time to resume the page for revise routine when the IO transfers is complete. So, in any case, we are faced with three major components of the page fault service time. So, first one is service the page fault interrupt, second one is read the page, and third, the restore the process. So first and third tasks can be reduced with careful coding to several hundred instructions. So these tasks may take from 1 to 100 microseconds. Its pH switch time, however, will probably to be close to 8 milliseconds. Okay, so the total paging time is about 8 milliseconds, including hardware and software time. Okay, so remember also that we are looking at only the device service time. If the queue of process is waiting for a device, we have to add device queuing time as we wait for the paging device for free to service our request, increasing even more the times to swap. So this is a performance of demand paging. So page fault rate is 0 is less than or equal to p or less than or equal to 1. If p equal to 0, no page faults. Okay, if p equal to 1, every reference is a fault. So E80, that is effective access time. So E80 is equal to 1 minus p into memory access. So plus p plus page out plus swap page in. So this is the example for demand paging. So we have to give a memory access time is equal to 200 nanoseconds. So average page fault time service is equal to 8 milliseconds. So E80 is equal to 1 minus p into 200 plus p of 8 milliseconds. So 8 milliseconds is an average page fault service time. Okay, so 1 minus p into 200 plus p into 8 milliseconds to be converted into nanoseconds. So 200 plus p into 7,999,800. Okay, so if one access out of 1000 causes of page fault, then E80 is equal to 8.2 microseconds. Okay, so this will slow down by factor of 40. Okay, so if we want performance degradation, so 10%, so 220 greater than 200 plus 7 lakhs 999,800 into P. So this is on one page fault in every 400,000 memory access. So this is demand paging optimization. So demand paging optimizations as in swap space IO faster than the file system's IO, even if in the same device. So swap allocated in large chunks, less management needed than file system. So copy your entire process image to swap space at process load time. So then page in and out of space swap space. So they use it in older BSD units. So demand page in front program binary on disk, but diskette rather than the paging out when the freeing frame. So used in Solaris and current BSD still need to write to swap space. So what next one is anonymous memory. So page is not associated with the file, which means like stack and heap. So this is anonymous memory and page modified in memory but not yet written back to the file system. So mobile systems typically don't support swapping, instead demand page from the file system and reclaim a read-only page. So this is the end of the slide. Uh, so what are the things we are learned about in virtual memory and demand paging? So just recall it, and thank you so much for watching this video.